So welcome you back. So let us do a recap of what we were doing, which was about scale invariant estimation. So before this we did location invariant estimation, and the reason why we are considering this location invariant estimation and scale invariant estimation is because for these kind of probability models, which are location or scale probability models, there is a very nice structure of the estimation problem concern. So one can apply the principle of invariance to restrict the class of estimators under consideration. Now, advantage of doing that is once you have restricted the class of estimators under consideration, there is a possibility that the best estimator might exist. And we saw that in certain location models, we were in a position to find the best location invariant estimator. So now let us do a recap of scale invariant estimation. So the formulation is as follows. So suppose x1, x2, xn is a random variable which may represent a random data. And suppose this has a distribution function f, which belongs to the family P, and this P is a parametric family of distributions. So it is indexed by a parameter theta, which is a real parameter, and in fact, this is greater than 0, f theta, theta greater than 0. So my f theta, x1, x2, xn is of type f of x1 by theta, xn by theta, where x belongs to sample space, which is whole Rn. So even in location case, scale case, you might have situations where support of x1, x2, xn is such that it contains the negative values of xi's. And that is the reason I am taking my sample space to be whole of Rn, so that negative values of xi's are also possible. And what is my parameter space? My parameter space is 0 to infinity. So to apply the principle of invariance, I have to search for appropriate group of transformations under which this problem remains invariant. So certainly I know that theta is positive. If I replace theta by any c theta, I still am in the same family. Now replacing theta by c theta is same as I can multiply both the sides by c, and then it remains the same. So that means if I consider f theta x1, x2, xn is same as probability under theta that x1 is less than or equal to small x1, xn less than or equal to small xn. Now this is same as probability. If I multiply by a constant c which is positive and I do it throughout, the inequalities are not going to change. So this is same as probability cx1 less than or equal to small cx1, cxn is less than or equal to small cxn. Let me call this as another random variable, which I am denoting by y1, y2, yn. And what are y1, y2, yn? They are nothing but transformation of x1, x2, xn through the transformation that each component is multiplied by constant c. So this is same as probability that y1 is less than or equal to cx1, y1 is less than or equal to. So this suggests that if possibly I consider the transformation y1, y2, yn, which is cx1, cx2, cxn, then things would be simpler. So let us try to see what is the probability under that y1 is less than or equal to small y1, yn is less than or equal to small yn, which is same as, now what I assume here is my c is positive, and that is the reason why inequalities are not changing. The reason for writing down this in this manner was just to get a hint, what should be the group of transformations. I have now got the whole that my group of transformations would be Cx1, Cx2, Cxn. So this same as probability that Cx1 is less than or equal to y1, Cxn less than or equal to yn. But C is positive, so this probability is same as probability that x1 is less than or equal to y1 by C, xn is less than or equal to yn by C. And what is that? That is nothing but the f of whatever is the argument divided by theta. Whatever theta is over here. So argument is y1 by C, that divided by theta is y1 by C theta. Yn by C theta. And what is this? This is nothing but f of C theta of y1, y2, yn. That is how f theta of x1, x2, xn is defined. So what does this suggest? This suggests if I consider my group of transformations to be C of x1, C of x2, of C of xn, their distribution is again in the same family, because if theta is positive and C is positive, so C theta would be positive. So this argument is again in this range. So that means this distribution is again in P. So what does that suggest? This suggests I should consider the group of transformations to be G of C, C positive, where GC of x1, x2, xn is same as, which are my yi's, right? Because they are the transformed variables. Cx1, Cxn, x belongs to Rn, which is my sample space, and C is positive. So this preceding discussion suggests that my problem is invariant. My family of distributions P is invariant. So P is invariant under G. Now this G induces a group of transformation on the parametric space which takes basically theta to C theta, with induced group of transformations on parametric space theta as G bar, which is G bar C, such that C is positive. And how this G bar C is defined? This G bar C is coming from here, because my transformed variable y1, y2, yn, which were nothing but Cx1, Cx2, Cxn, again have a distribution belonging to this family with theta replaced by C theta. So my G bar C theta becomes C times theta, where theta belongs to parameter space theta, which is 0 to infinity for every C. So my P is invariant. Now I have to see my estimation problem should be invariant. For that, first let us define what I want to estimate. One way is you can consider estimation of just theta. What we can do is we can consider estimation of, in general, theta to power b. So goal is to estimate theta to power b, right? B is not equal to 0, is a specified constant given to you. Under the loss function. L theta A, where theta belongs to parametric space theta, A belongs to xn space. What would be my xn space? Xn space should be any possible value of theta to power b. Theta is positive. So theta to power b is also taking only positive values, and in fact it takes, if theta takes value 0 to infinity, theta to power b also takes value 0 to infinity. So this is my xn space. So to make the problem invariant, the first thing I have to do is I have to identify what should be the group of transformations on this action space A. And how does one get an idea of what should be the group of transformations? One tries to look at, in the transform problem, what is the transformed estimate? Original problem, estimate was theta to power b. In the transform problem, theta to power b gets transformed to c theta. So, in the transform problem, theta to power b gets transformed to c to power b theta to power b. So, my transformed action should be c to power b times action A. So, this suggests that I should consider my group of transformations on action space G tilde as GC tilde. Where GC tilde A is nothing but c to power b A. A is in action space and c is positive. All right, and that's a natural choice for G tilde, and I've told you a reason why. Because in the original problem, I was interested in estimating theta to power b. In the transform problem, theta gets converted into c theta. It gets transformed to c theta. So this whole thing gets transformed to c to power b, theta to power b. This was an estimate in the original action. If the original action was A to estimate theta to power b, in the transform problem, the corresponding action should be c to power b into A. And that is what we have written down over here. So, L is invariant under G, because for problem to be invariant, L has to be invariant under G. What should happen? L theta A loss in the original problem should be same as loss in the transform problem with transformed action and transformed parametric value. Transformed parametric value is G bar C theta. Transformed action is GC tilde. For every theta belongs to theta, which is 0 to infinity, A belongs to A, which is again 0 to infinity, and C positive. So what does that give? This implies that L theta A should be same as L of G bar C theta is C theta. GC tilde A is nothing but c to power b into A. Now this should happen for every theta positive, A positive, and C positive. So what I can do is I can first fix rest of the things. I choose C to be, I can choose C to be 1 by theta, so that this becomes 1. So I fix, so that means this for any fixed theta and A, L theta A should be same as L of 1, and C is nothing but 1 by theta. So A by theta to power B. For every A greater than 0, theta greater than 0. So if my loss is invariant, this would happen, and you can see that if this happens, this anyway happens. So first let me add one more step. This implies that L theta A is only depending on theta and A only through the fraction A upon theta to power B. So that means L theta A is only a function of A upon theta to power B. So this is same as W of A to power theta to power B for every A positive, theta positive for some function W. And W certainly, its argument should be a takes value 0 to infinity, theta takes value 0 to infinity. So this should be defined from 0 to infinity. And since it is a non-negative function, it should take value in the closed interval 0 to infinity. If L is invariant, this would be of this type. The converse is straightforward. If L theta A is of this type, then what would be L of G bar C theta G C tilde A? You can see this becomes C theta C to power B theta to power B. A becomes C to power B theta to power, so they get cancelled, and this is satisfied. So the given problem is invariant under G with L theta A, my loss function is of the type W of A by theta to power B. A belongs to Xn space, theta belongs to parametric space, both are 0 to infinity. For some function W, which is defined from 0 to infinity. So as I said in the beginning of the course that it's reasonable to assume that my loss function is convex. And exactly that is what I'll do here. So I'll show that my W, L theta A, so I assume that W of e to power t is convex and non-monotone. I'll explain why we need this assumption. The idea is what I'll do is this W of A by theta to power B, I'll try to minimize W of log of this. So log of A minus log of, I'll come to that. So this for the time being you assume. So enough to, so you can take W to be also convex. In fact, if W you take to be convex, then W to power e to power t is convex or not. To see that, what you can do is you can look at psi t as W of e to power t is convex and non-monotone. So psi t is W of e to power t, psi prime t is W prime e to power t into e to power t. Psi double prime t is e to power t, W prime e to power t plus e to power t, W prime e to power t, e to power 2t. So note that just W as convex and non-monotone may not suffice, because that may not prove that W of e to power t is convex or not, because for W of e to be convex, psi double prime t should be positive. But what is happening over here is it is nothing but only coming out to e to power t, W prime e to power t plus e to power t, W prime e to power t. W is convex, so I know that this is positive. This I do not know. So just W convex may not do. So what assumption I'll need is W of e to power t is convex and non-monotone. And why such a assumption is required? It is straightforward to see, but the details I'll explain you later as when we reach to that step. So I'm trying to say that this assumption I don't need. I need assumption that W of e to power t is convex and non-monotone. Okay, so it would see that what would see when we are considering W of e to power to be convex and non-monotone, this would be clear that I'm only considering the non-randomized estimators. it suffices to consider non-randomized estimators. Suffices to consider only non-randomized estimator. So let us say DI is the class of all invariant non-randomized estimators. So it is a class of non-randomized invariant What does that mean? That means delta is in DI if and only if delta of my unit or data is transformed, so that means GC of X should be same as if my data was the original itself, except that now I have transformed my Xn. Xn is delta. So G tilde C delta X for every C and for every realization of the data point X. So what does that mean? This is equivalent to saying that delta of Cx1, Cxn is same as GC delta is nothing but, what is the GC tilde? It is same as C to power B into Xn. So that means C of B of delta of X1, X2, Xn for every C positive and for every X. Now note that this is a scenario where my Xi could be negative, but my C is positive. So I have, what I can do is I can choose C to be 1 upon X to power 1 by Xn, but C has to be positive, so choosing C as 1 upon Xn will not do. I'll have to choose C to be 1 upon mod of Xn. So this implies that delta of X1 upon mod of Xn, Xn minus 1 upon mod of Xn, Xn upon mod of Xn, C I have to written as 1 upon mod of Xn to power P. Note that Xn is equal to 0 is not an issue because Xn is equal to 0 happens with probability 0 because of continuous nature of the distribution. So delta of X1, X2, Xn for every C positive and for every data point X. So note that we are exactly following the same steps as we followed in the case of location invariant estimation.